Hello, am I audible to all? Hello,
Sir.
hello. So my screen is visible.
Yes, sir.
Please mute.
You please mute yourself. Good afternoon, everybody. So today is the now lecture session, but now is the tutorial sessions. So derivations of theoretical concept of Memristor Emulator. So in this derivations, we will see how we will derive the equations of Memristor simulators using CMOS circuits. So initially, I will discuss the theory. What is the memristors? So during 2 days of this lecture series, we found many different experts. So about the memristors, so memristors device we heard from Professor Kang, and today I have discussed in the first lectures in the first half about the memristors. So that was briefly. Now quickly I'm again repeating that things. Memristor is a fourth basic element. It is an electrical component that regulates the flow of electric current in a circuit or remembers the amount of charge that previously flowed through it. This is the basic definitions actually. This is predicted by 1971 and created by R.S. Williams in HP laboratory in 2008. So this is a nonlinear device, and at high frequency this behaves like a linear. Chua anticipated the missing link between charge and flux that proposed is the fourth basic fundamental element. So the relations between that charge and flux is mq equal to d phi upon dq. Okay, so the circuit based on CMOS technology to mimic the property of physical memristors have been commonly referred as a memristor emulator, because there are many technical difficulties in designing or fabricating the memristor device. So this is the fingerprint of memristor emulator. So here you can see pinch hysteresis loop. Pinch hysteresis loops is first and third quadrant, and loop area changes with frequency. You can see this. This is a red one, then another green one, and then light blue. So when frequency is increased, its loop area will decrease. Shrinks to a single valued function means when frequency is infinite, it shrinks in a single valued functions. At infinite frequency, this behaves like a linear resistance. So this three more important fingerprints, or you can say unique property of the memristor emulator or memristor. So emulator means we are mimicking the property of Memristor's device using the CMOS circuits. So this is the Memristor Emulator circuits. Now, so generations of different Memristor simulators. So first, researchers designed Memristors using diode and resistors. Using diode and few resistors we have used in the designing of the circuit. So got Memristor emulator. Then people used analog multipliers. So using analog multipliers, designed the idea. Then current mode building blocks. So current mode building blocks, you know that I already discussed in the previous lectures. So current mode building blocks have many properties, that low parasitics effect, low parasitics, less non-ideality in compared to voltage mode circuits, and many more low power, also low powers. You can easily design the current mode techniques, low power circuits. And now people are working Memristor simulators using few MOS circuits. So using 1 or 2 or 3 MOS, you can design Memristors. You can emulate the property of Memristor from CMOS. Here MQT is called memristance, which has been same scale of resistors in ohm. And W5T is a memductance, which has a same scale as conductance in Siemens S. So charge control memristors T5 equal to M dq upon dq, and flux charge control dq upon d5 omega W5 on d5. So these are the two different property we use to design the memristor, or two different equations for the charge control memristors or flux control memristors. We will use this idea in design of different categories of memristors emulator. Now, so in the first analog building blocks we will use in the designing of Memristor simulator is a OTA. So we need to detail about operational transconductance amplifier and few small applications. Thereafter, we will see the designing of Memristor emulator, CMOS based Memristor emulator. So now this is operational transconductance amplifier. So OTA is a basic building blocks of electronic systems. However, op-amp was the previously basic building blocks. Now OTA is also one of the current mode basic building blocks. It consists input and output impedance is high. Then function of transconductance is to convert an input voltage to output current. Here is the input voltage V plus V minus, or BP or VN. Some books BP and VN is available, and I out is the output current. So I out is expressed by GMVD, VD equal to VP minus VN, difference voltage. Okay, so transconductance amplifier can be configured to amplifying or integrate either voltage or current. Okay, this is the small signal model of OTA. This is a symbolic representation of OTA. V in plus, V in minus is the input, inverting and non-inverting. V plus or V minus is the 7 and 4th terminal is the potent biasing voltage applied to the circuit, where we will use, and I bias is the biasing current, I out is the 6th number pin. So this is the CA3080, which is available in the market. So here I out equal to GM upon VT. So I out is proportional to GM. So the ideal characteristics of this OTA is input impedance or input resistance is infinite. However, practical resistance in mega ohm range. R out is output impedance is infinite. bandwidth will infinite. These are the ideal characteristics. Practical is not that one. Practical is in mega-ohm range. So for perfect balance, I out equal to 0 and when V plus and equal to V minus. So this we can control. VD, I already told VD equal to V plus minus V minus, I out equal to GM VD. Therefore, I out equal to GM V plus minus V minus. So this is the equation of OTA and GM. Also, this GM is a transconductance. So we can tune this GM using biasing current. This I bias. So GM equal to IB upon 2VT. So I is proportional to GM in case of OTA. This is the BJT based operational transconductance amplifier. So here in this figure we can see internal structure. Q1 and Q2 is a differential pair formations. Q3, Q4 is a current mirror. Q5, Q6 is another current mirror. Q7 and Q8 is another current mirror. And Q9 and Q10 is another current mirror. So if you see this circuit very carefully, here this is the biasing current. This Q3, Q4 is one current mirror. So this IB is transferring to this IB here because this Q3, Q4 is a current mirror. Then this Q5 and Q6 is another current mirror. So this collector current of Q5 is transferring to collector current of Q6, IC1. So IC1 both are equal. Here Q7 and Q8 transistor is again current mirror. So IC2 and here this IC2. Here is IC2 is transferring this terminal because again this is the current mirror. Now if you see the circuit is Q9 and Q10 is another current mirror. So this IC2 is transferring here. So hence if at this node I out, IC1 minus IC2 is the I out current. So this is the description of BJT based operational transconductance amplifier. Now, if you see how we calculate the transconductance, so I already told I equal to GM V plus minus V minus, or we can say I out is proportional to VD and I out equal to GM VD, where GM is the proportionality constant. So here I out is proportional to V minus minus V in, and then I out equal to GM V in plus minus V in minus. Then we are talking about BJT based transistor. So collector current of NPN transistor, we know that IC1 equal to IB upon 1 plus exponential VD minus VT, and VD equal to V in plus minus V in minus. Then IC2 equal to IB upon 1 plus exponential VD plus into VT. So this is the IC2. Then IC1 minus IC2, we will get this one, IB 1 plus exponential plus VT minus 1 minus exponential minus VT divided by 1 plus exponential plus VT into 1 plus exponential VT. This is the IB. Then after analyzing the circuit, we becomes these equations, and these equations you already know. This is the 2 sine VD1 VT plus 2 cos VD1 VT. So which is equal to IB 10H VD upon 2 VT. Now if VD is far less than 2 VT, these are the conditions for linearity of the device or linearity of the operational transconductance amplifier. So IC1 minus IC2 equal to IB into VD upon 2 VT. So approximately I out equal to IB upon VD upon 2VT. So from this equation 1, I out equal to GM into VD, where GM equal to IB upon 2VT, which I talked in the previous lectures. So this was the GM. So we saw here, so how we will calculate the transconductance of basic building blocks OTA in this case. Now, in this case, I already told we can change this GM of the circuit. So if we see the internal structure of this circuit, so here RB, through RB we connected voltage V, 7.45 is connecting to, this is your 5.5 is connecting to voltage V, this one. Then after 5 and 7 connected, then you will apply the Kirchhoff voltage law at that point. So IB equal to 2V mod of minus VBE. So hence then IB equal to 2V upon RB. So this RB, this is your RB. If you change this RB, correspondingly your biasing current will change. So how you will set this how you will change the OTA transconductance using the biasing voltage available in the circuit. So this is the way, one of the way you can change the transconductance. Now next one is, so if you connect minus B, so when RB is connected to ground or minus B, so if you apply the Kirchhoff voltage law of that circuit, so minus IB RB minus BB plus B equal to 0. So IB RB equal to B minus BB. So IB equal to B minus BB divided by RB. So if let us suppose V equal to 15. So 15 minus 0.6 divided by RB. So IB equal to 14.4 divided by RB. So IB changes by controlling this RB now. So if you change this RB, if you put here potentiometer of the circuit, so this RB you will change, so your biasing current will change, and biasing current will change, so your transconductance will change of the circuit. And if you use that OTA in any analog signal processing circuit like filters, oscillators, or memristors, you can externally tune the gain of the transconductance gain of the circuit, which is very good property of the device, which is not available different places, different analog or like op-amp or another devices. Just wait, please. So sorry for disturbing. So this is actually one of the application of OTA. So this is the application of OTA. So in this case, so we can use as a inverting amplifier. So assuming OTA is ideal, so output current IO equal to minus GM VI. So this is the grounded. So current flowing through this RL is I0 equal to V0 upon RL. Hence, therefore, VO upon VI equal to minus GM RL. So this is actually the circuit. From that, we can get the output of inverting.
Basic note amplifier. I know. What? It's something. It's some chicken.
You can eat.
Oh, sorry, I was muted. So this is actually summer circuit. So summer circuit in this case, let us first we discuss this one. This is the ideal inverting amplifier. So here I out equal to minus GMVI and IO equal to VO upon RL. So VO upon VI equal to minus GM upon RL. So easily you can derive from this circuit. Now this is the summer circuit. So summer circuit is here three OTA have used here V1, V2, V3, three inputs are there. So this negative terminal is grounded and here two inputs have applied. So what is the output here? Here the output is G V1 and here G V2 minus V3. All are added here. Then here we will get VO equal to this one upon G V1 plus GV2 plus GV3. Hence V equal to V1 plus V2 minus V3. So this behaves like a OTA summer circuit. Now another applications is a floating resistance. So in floating resistance means we can use as any floated types of for a resistance. So how we'll use? So what is the use of this floating resistance? Because when you design the any circuits which wants to less silicon area, so that time we will use this type of resistance. So here if you see this I1 equal to GM V1 minus VT, V1 minus V2 and I2 equal to GM V2 minus V1. So I1 minus I2 will be GM V1 minus V2 minus V2 plus V1. So which is equal to 2 GM 2 V1 minus 2 V2 and then V1 minus V2 upon I1 minus I2 equal to 1 upon 2 GM, which is resistance. Now as per directions I1 equal to minus I2. So V1 minus V2 upon I equal to 1 upon GM. So by 2IB, both the GM can be controlled simultaneously. By 2IB, both the GM can be controlled simultaneously. So this behaves like a floating resistance. Now this is the how we will use this OTA as a inductor. So inductor is very important in the integrated circuit because inductor cannot be fabricated, it cannot be designed in the chip. So for that, so how we will get the inductor property from this OTA? This is the very important. So you can see that this current through CO, this is SC0 into V1 minus V2. Then output is OTA is this one. So here IC equal to minus IO. So then ICO V1 minus V2 equal to GM V1. Now current through RO we will get this current through RO we will get I1 equal to V1 minus V2 upon R0. Put V1 minus V2 from 3 2 into 4. So I1 equal to GM V1 upon SCRO. So V1 upon I1 equal to SCRO divided by GM V1, which is SLQ. Now, if you equate these things, you will get L equivalent equal to CORO upon GM V1. So now we can also use this OTA as a inductor. Next is a now. So up till now we have studied basic fundamental about the one block we have targeted, that is OTA. Now next is the next applications of this OTA in designing of memristors we will see here. So this is actually again the CMOS implementation of OTA. Here you can see these are the current mirrors and differential pair, and from this VB we can change the transconductance of the circuit. Now this is actually our work. Now this is here we have used one OTA and one inverter to design the memristor. Now here we will see the detailed equations, how we have solved the equations of these memristors. So the port relationship of this OTA is GM VP minus VN, where GM is the transconductance, and while in the BGT case we know that GM equal to IB upon VT, but here GM equal to, because this is the CMOS, so after the analyzing the circuit of internal structure, GM equal to K upon under root VB minus VS minus 2 VTH, where VS is a source voltage of M3 and VTH is the threshold voltage of M3 and M10. From this circuit you can see. So where K is also, we know that process parameter of transconductance. Then output of OTA is given by this Ix minus In equal to Gm. This is a 0 grounded into Vin. So therefore In upon Vin equal to Gm K under root 2 Vb minus Bs minus 2 Vth. Then also Ic equal to Id1 minus Id2. So differentiate, you will get this expression of the memdistance. Thereafter Vc equal to Vb equal to 1 upon Ic dt. So we have integrated this phi n upon Gm upon C we get. So thus it can be said that fine control the capacitor voltage in this circuit. It can be stated that capacitance is essential parameter in determining the memory of the circuit. Substituting VB from 16 in 13, we will get this one. Memductance In upon Vin K upon under root fine GMC minus Bs minus Bth. Since Bs is ground, so hence memductance is finally given that In upon Vin equal to W fine equal to K upon under root fine GMC minus 2 Vth. This is the final memductance equation. So here we understood that how we will calculate the memductance of this memristor circuit. Now we have done this simulation result using cadence Virtuoso 0.18 micrometer CMOS library. So power supply for this simulation we have used is plus 1.8 volt 0 to plus 1 volt. This is the aspect ratio we have used. So we get this OTA. This is the OTA at 38. Again, these are the OTA analysis of CMOS OTA outputs analysis of the GM versus VV graph, IZ versus VZ graph. Here the simulation result is shown here. So input setting of parameter is this one. Amplitude is 300 volt DC, offset 900 volt, input frequency of 10 megahertz. So here pinch hysteresis of 10 megahertz and transient response of 3 cycle is shown here, and state voltage curve is shown here. Setting a voltage of approximately 1.1 to 1.2 volt and reset voltage approximately 0.6 to 0.7 volt. Here is the pinch hysteresis loop of 5 and 10 megahertz, here 25 to 50 megahertz, and PHL of different process parameter. The working range of memristor is governed in figure 9, which already across the corner analysis shown of robustness of design of the process circuits. Now this is the simulation result, and this one is the non-volatile property. These two are the non-volatile property of the memristors which I designed. This is a layout, and layout area is 7452 micrometer squares. Here pre and post layout is overlapped, is some parasitic available, so there is some mismatch in pre and post layout. Now we are moving to the another circuits. This is the experimental validation of high frequency memristor emulator on 4 CTA frameworks and its application in Chow circuits. So here we have used 4 CTA Here two biasing current is available. Bx in minus B, Bx By is the input and these are the outputs. This is the block diagram of 4CTA. So here we can see that this portion is double C2, a triple C2. So in triple C2, we can change the current control second generation conveyor it is called. So we can tune the transconductance using this biasing current IB, and this is the well-known transconductance amplifier. So we will use this circuit to designing of 4CTA based Memristor emulator. This is the 4CTA based Memristor emulator. So here this is the port relationships and different equations. Now here we can see that the derivations V in equal to I in Rx plus Vy, and this Vy is IOR equal to where I0 equal to GM Bh2, Bz2 is the property of the 4CTA. So after analyzing these equations 7, 8, 9 is 7, 8 in equation 5 in this equation 5. So we'll get V in equal to I in here T Rx plus K R1 R2 QCTC INT minus K VSS plus VT R1 R2 into IN. This is the equation 9. So the grounded Memristor emulator equation has been derived in equation 11 using equation this 9. So we have divided the current V MQCT V in T upon I in T. So final Memristor equations is shown here. MQCT Rx plus K R1 R2 QCT C minus K V VT plus R2 R3. So this is the final Memristor's equations using this circuit. Only we applied here Kirchhoff voltage law, current law to getting the V upon I. Here V upon I, you will get the Memristor's equation. Now further, the final equation is shown this equation 11.1. Now for the examine the frequency response of Memristor circuits, we have derived the equations. So we get this substituting this 13 in equation 11. So Memristor circuit is obtained as this one Rx minus K VSS plus VT R1 R2 plus R1 R2 AM omega C Rx minus 1 BM plus VT R1 R2 cos omega T into pi. So this 14 number is after the considering the frequency response of the Memristor emulator circuit. See, these are the transient of MRE Memristor emulators at this is PHL at 500 kilohertz and this is the PHL at different frequencies. This is also at different resistance value 25 ohm, 50 ohm, 75 ohm, and this is the Monte Carlo analysis and PHL at different process corner. Here this is the layout of the 4CTA based Memristor emulator, and this is the simulation result, and this is the non-volatile property at decremental mode of the 4CTA based Memristor emulator. Now we have tried to do the experiment of this Memristor emulator. So we have designed this 4CTA based Memristor using 88.4.2 OTA we have used. We have done this into laboratories of the testings. We received this experimental result. This is a simulation based result and this is the experimental based result. Here this is the experimental setup of this corresponding result is shown here. This is the less frequency, this is the more high frequency. Now we are moving to the another circuit, Memristor emulator circuit using MOCC2. So MOCC2 block diagram of MOCC2 is shown here. So internal structure is shown here. So here MO means you have multiple output and so it is called multiple output current conveyor. And other property of current conveyor is same. Now this here we have used multiple output current conveyor and one multiplier. So if you see the equations, you can see V in equal to I in R1 plus Vx, V in equal to I in R1 plus Vy. So V in equal to I in R1 plus Vc and Vr2. You can easily understand from this equation. So V in equal to I in R1 plus Qc upon C into minus I in R2. V in equal to I in R1 plus Qc upon C into minus I in R2. So V in equal to I in into R1 minus Qc upon C upon R2. So V in T equal to 1 I in R1 minus QC upon C R2. So Memristor's equation is this one actually. And this is the port relationship of this MO double C2. Now to analyze the frequency response of Memristor emulator, we assume that input voltage V in equals to V in sine omega t, where V signifies the amplitude of the input signals and omega is angular frequency. Initially charge is 0, so R equal to this one. So V in sine omega t 1 into R1, I in equal to Vm sine omega t upon R1, dqc upon dt equal to Vm sine omega t R1. So dqc we have integrate V and Vm sine omega t into RT. So qct is this one. Vm omega R1 cos omega t pi plus C. So using initial condition at t equal to 0, qct equal to 0, so that 0 equal to Vm upon omega R1 cos omega cos pi plus C. So minus C equal to Vm omega R1 minus 1. So C equal to Vm upon omega R1. So QCT equal to Vm upon omega R1 cos omega t minus pi plus 1. So using 2 in 1, so we can get MQT equal to R1 minus Vm cos omega t minus pi plus 1 into omega R1C into R2. So this is the derived Memristor equation from based on MO double C2. Now, this is the transient analysis, V in versus time analysis, input voltage and input current. So this is the pinch resistance loop in the current voltage plane for varied frequency range from 9 megahertz to 40 megahertz. This is the frequency at 500 kilohertz at different picofarads capacitors. This is the pinch resistance loop in current voltage plane of different picofarads of capacitors at different frequency. This is 500 kilohertz. This is the 1 megahertz, and this is the 1000 megahertz at different capacitors value. This is another one. So 67, 10 picofarads and 1 picofarads. Now the pinch resistance loop of this FC is constant, so all are overlap one another, and this is the non-volatile of proposed Memristor simulators we have designed. So I'm telling like proposed. So you can see this is the spikes we are applying, but non-spiking period. This retains the value. Now next one is double C2 based high frequency Memristor model. So here, this is the internal structure of double C2. Again, this is the well-known structure. Many times I already discussed. What relations is same? Now, so here is the Memristor emulator circuit. Here we have used one double C2 and one MOS. So here equation 1 points to port relationship of double C2. Here Ix equal to Iz, Vx equal to Vy, and Iy equal to 0. So we can see Vx equal to Vy equal to V in, and Ix equal to Iz equal to V in upon R. So the conductance looking at the input ports emulator can be written as I in upon V in equal to Gm into Kp Vs minus Vg Vy. So Vg into Vc equal to 1 upon C Izt, which is equal to minus 1 upon C V in upon R into dt. So Vs and Vc equal to 1 minus 1 upon C phi in upon R. Since the value of the input voltage is 0, so substituting with we will get this one, the equations 7. Now, therefore, the Memristor equation, its final form can be written as W phi in equal to minus Kp or plus 1 Kp Ic1. To analyze the frequency response of the Memristor Emulator, we assume that the input voltage equals to Vm sin omega t, which signifies that the amplitude of the input signals omega is the angular frequency. Fine. So, which is equal to Vm cos omega t minus pi omega, substituting this 9 to 8. So, final Memristor equation written as minus Kp by V plus Kp on 1.c Vm sin omega t minus pi into omega r. This is the Memristor, final Memristor. These are the simulation result, time domain graph and voltage. And this is a PHL at 10, 20 and 30 megahertz. And this is a PHL at 40 and 60 megahertz. This is the layout of this circuit. And this one is the pre and post layout result of the circuit and variation of Memristor with input voltage. So this is again showing the non-volatile property of the circuit. This is the experimental setup. Transient response of 6.5 kilohertz with setup and PHL 6.5 with setup, this one, and this snapshot of oscilloscope depicting the pinch hysteresis loop. This we have done in our laboratory. So using the available MOS. Thank you. So any questions you can ask.
Am I audible? From the participants, any queries are there? They may ask. Sir.
Any queries you can ask.
Also, you may write on the chat box.
Yes.
Can you please show 2/3
chat box no
Sir, can you open the chat box, sir? You can see there someone is written something.
Can you please show
Hello?
2-3 most best circuit? Yes, Rupam.
Am I audible, sir?
Yes, yes. Hello?
Am I audible, sir?
Yes, yes. Are you getting my voice?
Hello?
Hello, hello?
Am I audible,
Yeah.
sir?
Yes, yes.
So someone is written here, sir, can you please show 2 or 3 CMOS based Memristor?
Okay, okay, I got it. Actually, Rupam, I will give few papers so that designs 2 and 3 MOS based circuit. Okay, here I have not, but I will show you. Take another questions.
Any other questions are there?
Hello, sir. Sachin is
These
here.
are the design related issues, 2 or 3 CMOS based Memristor. You can see there. So I think in that slide, sir has not included. If someone will ask another question, they may ask.
Hello, sir.
Yes.
Sachin is here, sir.
Sir, I think there is no any other queries here.
No. Sachin is asking. Sachin.
Thank you very much, sir. These
Sachin,
all slides
sir,
are
yes,
very
sir.
informative.
Tell Sachin.
Thank you, sir.
Okay, sir, I have read about the simulations. Sir, in PHL, we are drawing the graph between the voltage and current. So, sir, it is a DC analysis or the transient analysis?
It is a transient analysis. You do the transient analysis.
And then we have to plot the Lissajous pattern, right?
Yeah. Yes.
Okay, sir, got the point. Thank you, sir.
Okay, there is one information here that next lecture will be start from 5 p.m. This will be delivered by Dr. Uday Khambete from SCL. Okay.
Okay.
Because from tomorrow's schedule, I think there is a change here. So we are mentioning that at 5 p.m. sharply it will start. So you all are requested to join at 5 p.m. today.
Thank you.
Thank you. Thank you, sir.
Okay.
डाल दीजिए डिटेल डाल दीजिए भाई, डाल दें।
Recording.
चला गया।